I can see.
All right, good. Great. So let's start by, so I'm going to start with chapter 1 today. And chapter 1 really is entitled Stress. And the first two articles of this chapter, which we are going to do today, 1.1 and 1.2, they really deal with kind of a review from statics, which is for finding internal forces in a member. So what happens in a structural member is that you have external forces on it, and they cause some internal forces in that member. And those internal forces cause what we call, for example, stress or strain. So before we start talking about stress and strain, we want to see how to quickly review how to find internal forces in a member. This you did in statics. This was chapter 7 of your textbook in statics, internal forces. So my question 1 to you, I hope you all remember what are the 3 internal loads. When you take a section of a loaded member, what are the 3 internal loads you find inside? I want an answer. Anybody?
I know shear and normal.
Correct. Shear, normal. There's one more. That's a moment. That's called a bending moment. So whenever you have a loaded member and you take a section, there will always be 3 internal loads in there. What are those? N, V, and M. So N is the normal force, V is the shear force, M is the bending moment. Now, irrespective, you always have to show these 3. Most of the cases that we will be dealing with, you'll find that normal force may be 0 because of the kind of loading we will be dealing with. But you still have to show it and then put it equal to 0. You must remember, and this is a concept portion point also, that every time you take a section of a loaded member, it will always show you, it will always have 3 internal loads, and they are N, V, and M. So please always show these 3, and then we can find the 3 of them. This is what we want to review today, how to find the internal loads. That means N, V, and M. And what do I have on my PowerPoint? Let me follow that. So equilibrium and internal forces, that's what I just reminded you of. What are the internal forces? N, V, and M. Then I have, the goal here is to determine internal loads in structural members. And how do we determine that? The purpose of this internal load is to determine stress. And so how do we determine stress once we know the internal load? This we are going to talk about tomorrow. Today what we want to do is review how to find the internal loads. And basically the procedure is very simple. You determine support reactions. And I'll show you that in some cases you don't even need to determine support reactions, but in some cases without determining support reactions you can't find it. So just take it as the first step always to determine support reactions. And the second would be draw a free body diagram, take a section where you wish to find the internal loads, and then apply equations of equilibrium to determine unknown forces and moments. So I am going to solve some example problems, and before we do that, before we do that, let's look at review another important thing, which is support reactions. So In two dimensions, these are the most important support reactions. This is, for example, a cable, and the cable is replaced by, hang on a minute, I want to admit somebody. A cable is replaced by one force in the direction of the cable. You see that? This type of reaction is called a roller. Roller is also replaced by one force. It is replaced by one force. It just why is it replaced by one force? Because it restricts translation only in one direction. For example, in this case, can I move my member in the X direction, which is this direction? I want an answer. With this support, can I move my member in the X direction? Yes or no?
Yes.
Yes, we can. So therefore, the only translation which is restricted is in the Y direction. I cannot move it in this direction. That is why you show one force only. There is no force in the X direction. But like I always say, this kind of logic you don't have to apply every time. All I need you to know is that as soon as you see a roller, just apply one reaction there. Roller will always be replaced by one force. And a smooth support also replaced by one force, but that force is perpendicular to the support. You see that? It is perpendicular to this support, the surface on which you are showing that support. So it's not perpendicular to the member, it's perpendicular to the support, the smooth support. So all these three that I've shown you, a cable, a roller, and a smooth support, they are replaced by one force each. And the next one you see is a pin joint, and a pin joint is replaced by two forces only, one force in X direction, one force in Y direction. And so blindly just replace a pin joint by two forces, always, always, always. This is another example of a pin joint is shown there. This is called an internal pin, this is called an external pin, but they both have the same two reactions. You have to replace them by Fx and Fy. Then the last one and the most restrictive one is called a fixed support, and the fixed support is replaced by, in two dimensions, it is replaced by three loads, which are two forces and one moment. I hope everybody remembers that. This is given in table 1-1 of your text also. We will be using these when we solve problems, and also distributed loads. So let's go on to the first example problem. Let me just admit this one more person. I will remind you, please try to be in time. It really disturbs the class every time a new person is trying to enter. If you can be here at 9:53, 9:55, you can well be here at 9:50, I'm pretty sure. So try to be here in time. It will be simple for you. You will not miss anything also, and it will not disturb the class also. All right, let's move on then and do an example problem. We just talked about these. Here is the example problem I want to do, the first one. Please read the problem. So what you see there is, let me ask you, what type of a beam is this? Anybody?
Fixed.
We don't call it a fixed beam, no. There's a technical name. There are three types of beams, and this is the third. This is one of those. Anybody else? Do you know what type of beam is this? Well, let me remind you, this is called a cantilever beam. It's fixed at one end and the other end is hanging free. So there are really two type of beams basically, one which is supported at both ends, and probably the next problem we do will be that type. That is called a simply supported beam, and this one which is fixed at one end is called cantilever beam. So this is a cantilever beam you see there. What type of loads does it have? Well, it has a distributed load from point B to point C, and it has a point load at point D. So it got both a point load and a distributed load. Now, the man is asking you to find or determine the resultant internal loadings at point B and C. And then he clarifies that point B and C, which are located just outside the rectangular load. So they're not right at this point, just a little outside. B would be right there, C would be outside of this, so somewhere there. And we will assume this to be at 5 meters distance also. So if we want to find internal loads at these 2 points, the very first thing we need to do is to find the support reactions. Like I said, you can get away without finding, even in this case, you can start from the right hand side and not find support reaction, but I'll anyway solve the problem by finding support reaction, so that is also a good review for you. Now, before I go to my board, my question, can everybody see my whiteboard where I'm going to solve the problem? I want some answers. Yes?
Yes.
All right, thank you. Let me move on to the board and so where's my razor? Oh, there it is. So problem one, no, this is not working.
Oh, crap.
To find the support reactions, we need to first of all draw the free body diagram replacing the support by its reaction. As we just saw, a fixed support will have two forces, one moment. So here is a free body diagram. I'm trying to draw a free body diagram to find the support reactions. And this being a fixed support, this is the end A. That's the end A, that's the end B. So here I got two forces, AY and AX, and a moment that I'm going to call MA.
Excuse me, Professor.
Yeah?
Could you move the camera a little bit to the right, to your right side?
Is that what you want?
Yeah, a little bit more. That's good. That's good. Thank you.
More people waiting. All right. So that's the fixed support. Then I got a distributed load, and I'm going to that distributed load is from B to C, and this I'm going to replace by one force. What will be the value of this force?
100.
500, thank you, because it is 100 per meter and then 5 meters. So this is 500 newtons. And then I got a force of 100 newtons at the other end there. So first off, what about AX? What can we say about AX? By inspection, I can say AX is 0. Why? No other X force. You can also write this by taking some forces in X direction equal to 0, writing that equation. This will be the only one. AX, there is no other force. So even if you don't write this equation, just show it and put it equal to 0. That's acceptable to me because it will happen a lot of times. So just you don't have to write this equation, just put it equal to 0. It's understandable. Now, what about the other equation would be some forces in y direction equal to 0. What does that give me? It gets me AY is in the positive direction, minus 500, minus 100 equal to 0. Therefore, AY is equal to 600 newtons. What about MA? To find MA, we can take moments at A. And if we do that, sum of moments at A equal to 0, will get me what? The first moment is this itself, and this is a counterclockwise moment as I have shown it. So this will be positive. I'm going to keep it positive. And then the next one would be due to the 500 force. What will be the value of that moment? 500 times the moment arm. What's the moment arm from 500? Anybody? So the weight, 7.5, correct? Because this is 5, and this is also 5, and this is also 5, but this will be acting in the center. So this will be about 2.5. So this moment arm is 7.5, and the moment created by this will be a clockwise moment. The clockwise moments we consider by sign convention negative. So I will put minus 500 times 7.5. And then the last one will be due to the 100 newtons force, and that will be, what's the moment arm for that? 5 plus 5 plus 5, 15. So it will be also a clockwise moment, so minus 100 times 15. And this will be equal to 0. This is the sum of all the moments. Everybody good? So from here I can find MA is equal to, writing material is failing today, I don't know why. MA is equal to, I take these on the other side, this becomes 1500. And this would become what? Plus 750 times 5. 750, is it? I got the numbers somewhere. Yeah, this comes out to 5,250 Newton meters. That's MA. So the first step in these problems is to find the support reactions. And I have managed to find the support reactions now. The support reactions are AY is 600 newtons and AX is 0, MA is 5250 Newton meters. Everybody good with this? This is step 1. Once you have done this, then the next step is to take a section at the point where you are interested in finding the internal load. So let's say we want to first find the internal loads at point B. Then I'm going to, this is point B somewhere here. I have to take now a section at this point B, somewhere there. let me do that. And once you take that section, you have to draw the free body diagram of that section. I'm going to make some space. Oh, it's not working nice. Yeah. So if you take a section at B and then draw the free body diagram, it will look something like this. So there's where B was. I took a section there and I found the support reactions to be. The AY was 600 in that direction. And MA was, we found it positive, yeah, right. So MA was 5250. This is now where I took the section. And when you take the section at point B, what do you expose? You expose all the internal forces. And the internal forces there are N, V, and M as usual. So there will be an N, which I'm calling NB. There will be a V, which I'm calling VB. And there will be a moment, which I'm calling MB. And these are the internal loads that I want to find. What are the internal loads due to the loading on that beam, which you saw, the point load and the distributed load. So the first thing you can notice once again is that NB is going to be equal to 0, because there is no other force in the X direction. Like we saw the last time for AX, similarly, this will be equal to 0. So that I have already found. NB is 0. I got two more things to find, VB and MB. To find VB, what do? We take sum of forces in the Y direction. Some forces in Y direction equal to 0. That will get me what? This is a positive force, 600. And this is a negative force, minus VB equal to 0. Therefore, VB is equal to 600 newtons. And to find MB, what do? We take moments. You can take moment at this point or this point. My recommendation to you, always go for the moments at the section. So this is the point I'm going to take the moments, sum of moments at point B equal to 0. That will get me what? The first moment is MB itself. And this moment is positive or negative? Anybody who can answer. Is MB positive as shown or negative?
Negative.
It is negative because it's a clockwise moment. So I'll say minus MB, and then will this contribute to the moment at B? No, because it is passing through B. The moment arm is 0, so it will not contribute. How about this one? This is already there, 5250, and this is the positive moment, so it will be plus 5250. And then there will be, the third moment would be due to this force, which is 600 times this moment arm. How much is this distance? 5 meters. So it will be, and this will be also a clockwise moment, so it will be negative. I would say minus 600 times 5. We took care of that, we took care of this, we took care of that, and nothing else will count. So this is all we have. This is equal to 0. And therefore, if I take MB on the other side, I can say the moment at B will be equal to 5250 minus 3000, and this will be 2250. My moment came out positive, which means that the direction I assumed for the moment was correct. So I can also say that this MB is equal to 2250 Newton meters, and this will be a clockwise moment as shown there. Any questions, anybody? This is the way we find internal loads at any point that we are interested in. So if we were interested in point B, what we did, we first found the support reactions. Then we took a section at B, and we just, after taking the section, we drew the free body diagram of the cut section, and we exposed the internal forces N, V, and M. And then we put the support reaction that we just found, and then we applied equations of equilibrium to find the unknown forces, internal forces. That's the way to go. So now the next thing is we need to find it for point C. Exactly the same procedure. You could again draw a free body diagram as we just did. But what I'm going to do is I'm going to find the internal loads at C by considering the right hand side of the beam. Well, I'll take a section at C, but then I'll use the right hand side. Let me show you what I mean. Maybe I can show you here. Can you see the lower half of the board? So here's my original beam, and it's fixed on this side, cantilever there. I got 100 there. I got 500 there. Now I want to find at point C, which is somewhere there, you see. So I have to take a section at point C like that. I already have the support reaction. So I have two options. When I take the section, either I can draw the left-hand side of the beam across the free body diagram, or I can use the right-hand side of the beam. Which one seems easier to you? Obviously, the right-hand side. So that's what I'm going to do. I'm going to show you that you could have, in this particular example, you could have found both the internal loads at C as well as B by considering the right half, and you won't have to find the support reaction. This is what I was saying, that in some cases you can get away without finding support reaction, but in some other cases you always have to find support reaction. So if you understand when you want to find and when you don't want to find, you can use that and avoid some extra work. In this case, we already found the support reaction, but just to show you how to use the right hand side or how to find the internal loads in some cases without finding the support reaction. I won't need them, because if I draw the free body diagram of the right hand side, this is how it will look. Let me show you. So if I take a section at C and draw the free body diagram, it will look something like this. So this is my section at C. I got 100 Newton force there. That's it. And what else is I have to show? Now the internal forces that I have exposed there at point C, they will be what? NV and M, always show the three. This will be NC, and this one you can show VC, and this one you can show as MC. N, V, and M. So that's the free body diagram from the right hand side. So I will not need the support reaction here. I can directly find. To find, for example, the first thing I can say is NC is equal to 0. Why? Because there is no other force in the x direction. So I don't need you to write the some forces in x direction equation. You can just quickly show me that you know NC will be equal to 0. I'll accept that. The second one would be some forces in y direction equal to 0. What will that equation give me? So VC is in the positive direction, VC, and 100 is in the negative direction. Minus 100 equal to 0. There is no other force in y direction. Therefore, we find VC is equal to 100 newtons. Then the next thing is we want to find MC. Once again, we have to go to the third equation, the moment equation. And like I said, I always suggest you to recommend that you can take moments at this point or this point. It's the best to always do it at this section. So sum of the moments at point C equal to 0, it will get me what? The first one is the moment itself and it is counterclockwise, so it will be positive, MC. And will this contribute anything to the moment at C? No, because the moment arm is 0. The only other one would be 100. What is this moment arm? This distance is 5. Yeah. So will this moment be positive or negative 100 times 5? It will be negative because it's going to be a clockwise moment at C. So it will be clockwise moments by convention are taken negative. So I'll say minus 5 times 100 equal to 0. Therefore, MC is equal to 500 Newton meters. As shown, it came out positive, so it is going to be counterclockwise as shown there. Any questions, anybody? So we found both answers. The man was asking us to determine resultant internal loading at point B and C. Point B we found earlier, point C we have found them now. What are the internal loading at C? NC is 0, VC is 5, VC is 100 in the upward direction, and MC is 500 Newton meters counterclockwise. That's how you find the internal loads at any point of a loaded beam like this. Any questions, anybody? All right, so everybody good? There is one person waiting to join. Let me admit them. All right. If you don't have a question, I can move on to the next example, which is going to be this.
Professor, just a quick question about the lecture in general. Will you be posting videos of the lecture?
Somebody asked me yesterday also. I am not sure if I put the record on today. I'll see if it is there. And I haven't yet worked out how to upload because the files are about 50 MB when the 1 hour lecture is recorded. And Blackboard refuses to accept that big a file by normal methods. I may have to zip it up or do something. I haven't worked out. If you guys are interested, I'll try to do it for you, all right? But the PowerPoints are already there. All right, let me go to the next example, which is this. Please read the example problem as I prepare my little board for this problem. A quick question from me also. Were you able to read the things I was writing on the board clearly?
Yes, sir.
All right, good. So let's do problem 2. Again, the first question is, what type of beam do you see in this problem? Good one. Yeah, I agree. But I just told you that this type of beam, which is supported at the two ends, is called what? A simply supported beam. Please remember. So this is a simply supported beam. It's supported at the two ends. What type of loads does it have? Well, the first one you see is a triangular distributed load, and then there is a couple moment acting. There is no point load in this. So, and the man is asking you to determine the resultant internal loadings at points B and C. Point B is located just to the left of the applied torque. So just almost at 500 foot-pound at point, that's point B. But, and then C is at the middle of the triangular load. Now, my first question to you, do you think we will need to find the support reactions or we can get away without it? Think about it. The thing is that let's look at point B. If I'm going to find the internal loads at B, I will have to take a section at B and then either consider the left-hand side or the right-hand side. If I consider left-hand side, I will need the support reactions at A. And if I consider the right-hand side, can I get away without any support reactions? No, then there will be the D. D support reactions will be required. So in this problem, you cannot solve this without finding support reactions. Do you see what I'm saying? As opposed to the last problem that we did, where we could have avoided completely finding support reaction. In this one, you cannot. You have to find the support reactions, at least one of them. So if you find, let's say, support reaction at A, then I take a section at B, and I draw the free body diagram of the left-hand side. And when I want to find at C, again, I will have to take a section, I'll have to draw the free body diagram of the left-hand side if I have only found the support reaction at A. So let's start by finding support reactions. Actually, I'll give you a couple minutes. You can do it on your own, or you can follow me around. So I'm trying to find the support reactions here. The first thing to do is to find support reactions. I have to draw the free body diagram of the beam, and that will look something like this. So there's my beam. And I have to replace my supports by their reactions. So at A, I will have, it's a pin joint, so I will have two, AY and AX, for example. Diagram. That's AX and AY at point A, and then I have, on the other end, I have a roller, so I put just one reaction there, DY. And then I have the other 2 points, B and C. At B, I have a counterclockwise couple moment of 500. What is it, pound, foot? Yeah, foot pound. And at D, I have a triangular distributed load, which looks like this. Let me see. So it extends 3. This was point B, all right, but this is not B. This is the 3-foot distance. So I have a triangular distributed load there, like that, which I'm going to replace by a point load. What will be the value of this point load? That's a question I want somebody to answer.
Yeah.
What will be the value of this point load? Correct. How do we get it? By finding the area under the distributed load. Area of this triangle would be, this is 3 feet, and this is given as what, 100 pound per foot. So area would be 1/2 times base, which is 3, times height, which is 100. So this becomes 150. In other words, this force, this load is 150 pounds. What point will this be acting? So what's the distance between from this end D to this point? Anybody?
2 feet.
It will be 2 feet because for a point load, we know that it acts at 1/3 from the tall end, 2/3 from the pointed end. So 2/3 of 3 would be 2 feet. This is 2 feet and this is going to be 1 foot. Everybody with me? Now the man says that point C, it lies in the middle of the triangular load. So middle means, where will point C be lying? Maybe I can use a different color just to show it. For instance, C would be right in the center there, and this distance would be 1.5. You see what I'm saying? That's point C. So first I want to find the support, the internal load at B, then I want to find it at C. But right now I'm trying to find the support reaction for which I've drawn this free body diagram. So the first thing you can say about, what can we say about AX? AX is simply equal to 0 because there is no other force in that direction. So what about AY and DY? How can we find that? Well, some forces in Y direction equal to 0 will get me an equation which is AY positive plus DY positive. And what will be the negative forces there? Will this count? No, this is a moment. The only one that will count is this, which is minus 150. Minus 150 equal to 0. So this is one equation, two unknowns. I cannot therefore find anything out of this. I still have to take moments. Where do you want to take the moments? Let's say we take moments at A. In that case, if you take sum of moments at A equal to 0 gets you what? So this AY will not contribute anything. The one moment we see there is 500. Is that positive or negative? That's a counterclockwise moment, so positive 500. And then this will contribute how much? 150 times. The moment arm will be how much? Will it be 7 or 7.5?
It'll be
Seven.
7.
7 because the force is acting at 2/3 the triangle.
Correct. So 7, right? 3 plus 3 plus 1, yeah, 7. So this 500 was positive. What about this one? At A, it will be counterclockwise, so it will be clockwise, so negative, minus 150 times 7. And then dy will have a positive thing, positive moment, so dy times plus dy times, what will be the moment arm? 9, all the way, equal to 0. And this brings me to, from here I can find dy. What will dy be equal to? Dy will be equal to 150 times 7, which will be
1050.
1050 minus 500 divided by 9. How much does that come out? 550 over 9. And this comes out to 61.1 pound foot. No, pounds, actually. This is the force. All right, everybody good? Okay, so what will be AY then? AY we can also find, which will be, you know, AY plus DY is 150. So AY will be 150 minus DY minus 61.1, which will be
88.9.
88.9. Thank you. So we found both the support reaction. Actually, all the three. AX is 0, AY is 88.9, and DY is 61.1. So now we can draw a kind of a fair free body diagram in which we can show the AY and DY as they are. Let's do that. Step 1, find the support reaction. We have done that. So let me now draw the free body diagram with the support reactions showing. And it will look something like this. I got that simply supported beam. And AY we found was 88.9. And DY we found was 61.1. And then we had at B, we had a 500 pound foot moment, and we also had a triangular distributed load there, which we replaced by one force, which was 150 pounds, acting at 1 foot from this side, 2 feet from that side. And point C, by the way, this is again 3 feet, the whole thing, but point C lies at the center. So this is 1.5 on either side. Everybody good? So when we want to find the internal loads at B, and the man says that B lies, if 500 is acting there at this point, then B lies just to the left of this, somewhere there. So if I take a section at B and then draw the free body diagram of that section, it will look something like this. That's point B. I got 88.9 here. And will 500 show on this or not? That's my question to you. No, because 500 is beyond B. So I'm not showing that. What I'm going to show are the internal loads which have been exposed now. They are no more internal. So this will be the normal force at B. There will be a shear force at B. And there will be a moment at B, and you can show the moment any way you want, but let me show it like this, MD. So now I'm trying to find the internal loads at point B, which lies just to the left of that applied moment. Now from this free body diagram, what can we say? Well, the first thing we can say is always is that NB is equal to 0 because there is no other force in that direction. And to find VB, we take some forces in y direction equal to 0. And that gets me, this has the positive one, 88.9. This will be the negative one, minus VB equal to 0, or VB is equal to 88.9 pounds. We have found two of them actually. NB is 0, VB is 88.9. And then what about how do we find MB? Well, you got to take moments at the section, for example. So some moments at B equal to 0 will get me what? If I'm taking moments here, this is the first one, which is counterclockwise, so positive MB. And then this will be a clockwise moment from 88.9. What is this distance? Should be 3 feet. So MB, and this is going to be clockwise, so minus 88.9 times 3 equal to 0, or MB equal to, how much does that come out, anybody? I got a number 2 somewhere. Yeah. 266 point, thank you, 0.7 pound-foot. So we found the internal loads at B. They are NB equal to 0, VB is equal to 88.9 downwards, and MB equal to 266.7 pound-foot. Now we got to find the next thing we got to do is find the same internal loads at point C. And to do that, we will have to take a section at C. And where is my C? This is my point C. So if I take a section there, I have the option now. I can draw either the left-hand side or the right-hand side. Because I have both the loads available, both the support reactions available, I think it will be easier if I draw the right-hand side. What do you say?
Dr. Braza, I have a question real quick.
Yeah.
So based off our VB, our direction is placed downwards and we get a positive number. Does that mean that we have 88.9 pounds going downwards or 88.9 pounds going upwards?
No, going downwards.
Okay, I was just clarifying.
Yeah, it's positive with respect to this diagram.
Okay.
And just to remind you, now that you reminded me of this, the sign convention for equations of equilibrium is that upward positive, downward negative. Towards the positive x direction, positive, in the negative x direction, negative. And moments, we have decided clockwise moments, negative, counterclockwise, positive. Those were the sign convention. That was the sign convention for equations of equilibrium. But for the internal forces, N, V, and M, the sign convention is different. And according to that sign convention, this VB is also positive. Do you remember that? Well, I don't want to say any more. I may talk about it later on tomorrow or something because I'm running a little short of time. So, but remember that there are two sign conventions we follow when we talk of internal loads. One is the sign convention of equation of equilibrium. They are positive x positive, positive y, upward positive, and counterclockwise moments positive. But there is another set of sign convention for N, V, and M, according to which this VB is positive, this MB, which is anyway counterclockwise, also positive, and this NB is also positive. So we'll talk about it some other opportune time. Let's now take a cut section at C, and I'm going to use the right-hand side. So I will draw the free body diagram of the right-hand side, which will look something like this. So I got a very small thing there. Took a cut section there. This is point C. So I got 61.1 there. And then I got a distributed load, which I cut off like this. So this is still there, the distributed load. And if I want to replace it by a point load, it will be something like this. Now I have really cut off the distributed load there, you see. What is the value of this? This was 100, am I right? Yeah, this was 100 and this was 3 feet. So if I'm at 1.5 feet, how much will this be? By similar triangles, you can show that this will be 50 pounds, not 100 anymore, it will be 50 there. And this distance is, we are saying C lies in the center, so this is 1.5. So this is 1.5. How much is this force then? This will be the area of this little triangle, which will be 1/2 into the height, which is 50, into the base, which is 1.5. And this comes out to how much? 25, and 25 times 1.5 would be 25 plus 12.5, 37.5. So this force is 37.5 pounds. Everybody good? Not a big deal there, but you have to know that this, how did we find this? We use similar triangles. These two triangles are similar. So if this is 100 for 3 feet, then for 1.5 feet, it will be 50. So from similar triangles, first we found that, then we replaced the triangular load by a point load, finding the area of that triangle. And now, once we took the section, we have exposed how many? N, V, and M. So there will be NC, and there will be VC, and there will be MC. Those are the 3 internal loads that I exposed. What can I say about NC? NC is equal to 0. No other force in x direction, so I can directly say NC equal to 0. What about the others now? Let's try to find the others. So to do that, we do some forces in y direction equal to 0. That gets me what? This is, for equations of equilibrium, this is positive VC. And then the only other one is minus 37.5. And then another one plus 61.1 equal to 0. These are the 3 forces in y direction. 1, 2, 3. I have taken into account all 3. And this really replaces the triangular distributed load. So as we have taken care of all the forces. Therefore, VC is equal to minus 61.1 plus 37.5 equal to minus, and it came out to minus 23.6 pounds. And what does this minus sign show?
That VC is acting downwards.
Exactly, thank you. So the direction we assumed for VC was upward, but actually the negative sign shows that it is going to be acting downward. You can also say the book uses this kind of thing sometimes. VC is equal to 23.6 pounds, and then he says downwards. So now to find MC, what do? We got to take moment at, and the best way is to take moments at C. Let's do that now. Sum of moments at point C equal to 0. What will that get me? Well, the first moment I see is MC itself, which is shown counterclockwise, so positive. MC. And then this will not contribute anything, these two will. So what will be the first moment would be due to 37.5 and it will be clockwise, so negative 37.5. What will be the moment arm for this? That's a question. What will be the moment arm for the 37.5 pound force?
0.5.
0.5, thank you, because it will be acting 1/3 of 1.5 from the tall end, which will be 0.5 there. So it will be minus 37.5 times 0.5, and then the moment due to 61.1 will be counterclockwise, so positive 61.1, and the moment arm would be this whole distance, which is 1.5, like that, equal to 0. This is the moment equation at C, and therefore I'll say MC is equal to, and if you take both of these the other side, you find MC will come out to be it will be negative, yeah, minus 72.9 pound foot. And what does that negative sign mean again? That MB is not going to be, MC is not going to be a counterclockwise moment. It is actually going to be a clockwise moment. It is the opposite direction. This negative sign shows. So you can say MC will be 72.9 pound foot. Let's show it counterclockwise. It will be actually clockwise. All right, everybody good? So we found the internal loads both at point B and point C. Wow, I already overstepped by 5 minutes. I'm sorry, guys. I didn't have my time in front of me. Well, the third example I have is really simple. I can just verbally do it in a minute and then let you go. And that is this. So determine the resultant internal torques at point A, B, and C, which are located just to the left of the applied torque. So point A is just to the left of applied torque. That means on that side, if you take a section there, you can see you will have to draw a free body diagram of this. Maybe I can do this example tomorrow before I start with stress. I'll take it up tomorrow. And I'll let you go now. This was a group problem solving. You can try it in your own time. And this is your suggested work for tonight. You got to read text articles 1.1 and 1.2. Got to do these yellow pages. These are the solved examples, 4 solved examples on how to find internal loads. And lastly, homework problems, 2 homework problems, chapter 1, problem 9, and problem 10. So this PowerPoint is already uploaded for you. You can go